Okay, so now let's consider the distribution of sample mean. So our first result is that if I have a population that is normal, then my sample mean would also be normal. Okay, so this completes our requirements for calculating the probability we mentioned in the previous video. Okay, for each random sample, as long as I know its sample size, the population mean, and the standard deviation sigma, then I actually know its the sample means distribution. As long as the population is from normal, then the sample mean would also be normal with mean mu and the standard deviation sigma over square root of n. Actually, the mean and the standard deviation is for any distribution. For any distribution, we have them. It's just that now we need a normal population so that my sample mean is also normal. So let's go back to that particular example. We want to calculate the probability for me to be punished. Okay? Now the good thing is that I know the distribution of the sample mean x bar is a normal distribution with mean 2 and a standard deviation 0.1. Okay? So all I need to do is calculate the probability for x bar to be that small and for x bar to be that large. And then the sum of them can be easily calculated by Excel or by any other software as around 4.5%. Okay? Please keep in mind that we can do this calculation because we know the distribution of x bar. Knowing only the mean and standard deviations are not enough. Okay? And knowing that x bar is normal is also not enough because we still need the mean and the standard deviation. So we need to combine all this information so that we can do this calculation. Okay, so if that's the case, let's do some further analysis. For example, we may want to adjust our standard deviation sigma by, for example, paying more or paying less attention to our production process. And that's going to change the probability, right? That's going to change the probability. So I may adjust sigma. If sigma gets larger, then the probability of getting punished will be larger. Or if sigma is smaller, then it will going to be smaller. So actually, for any sigma, I'm going to be able to find the distribution of x bar, right? Because the standard deviation of x bar is always sigma divided by square root of n. And then we may actually take a look at this kind of graph and optimize sigma. Like at the beginning, we have sigma which is 0.2, and we can calculate the distribution and calculate the probability of punishment as around 4.5%. We do see that when we decrease sigma, it's going to decrease the probability of being punished. And from 0.2 to 0.15, that decrement is significant. But from 0.15 to 0.1 is not going to be that helpful. Okay? So being able to calculate and draw this line is going to help us determine the optimal degree of maintenance and optimal degree of sigma. On the other hand, we know there is an officer, right? The officer knows that if the sample size is 4, then the probability of punishment is 0.045. So that means the officer may want to increase the sample size so that the chance for it to make some error determination would be decreased. So we can also draw a curve that maps each value of sample size to a probability for me to get punished. Okay, so that's also reasonable. In practice, you may want to ask, in practice, actually, we don't know mu, we don't know sigma, right? Then what should we do? The thing that we will do is that, well, if mu and sigma is like this, then my probability of getting punishment is that small. So that means if this probability is so small, but I still see this result, I'm going to what? I'm going to have some conclusion that the mean and the standard deviation is not like that. Actually, this would be the topic in the next lecture, so let's stop here. Now, you just need to know that given population mean, given population standard deviation, how to calculate some probabilities with respect to X bar. Next lecture, we will talk about how to go from a sample result to the population. The last thing is that what if our population is non-normal? In that case, the sample size is not normal in general. But as long as our sample size is large enough, then we still can use the central limit theorem to say that our sample mean is approximately normal. Okay, so there are some words. If you are interested, you may want to read. But the concept is actually very simple. As long as we have a sample whose sample size is large enough, then we can say our sample is normal. And that has nothing to do with the distribution of the population. Okay, so let's get the idea with some experiments. Consider our wholesale data again, and we know there is a variable called fresh. And if we draw the histogram of fresh, we can see obviously the population is not normal. Okay, we have a right tail probability. And in that case, we want to test central limit theorem by taking samples from this population. Okay, and then try to see whether we are doing right or wrong with our central limit theorem. So the thing is that here we have the population distribution, and then for each study, we take a specific value of n and draw about 5,000 do 5,000 times of experiments. In each time, we sample two values from the population and calculate the sample mean and draw it. Okay, when n is still 2, it's not that different. But when n is 5 or when n is 20, we gradually see that the sample mean gradually look like normal. Okay, when n becomes larger and larger, our sample mean becomes more and more approximately normal. If our population is not that skewed, instead if our population is actually close to uniform, then when n is 2 or when n is 5, then the sample mean looks pretty normal. Or when n is 20, then it's almost perfectly normal. Okay, so this is going to be helpful as long as we want to use the sample mean to do some inference. Okay, because we know as long as n is large enough, then the sample mean can be considered to be normal. And that's pretty good. So, in short, we're saying that given any population, if we want to do something with sample mean, then as long as our sample size is large enough, we can say our sample mean is normal. Okay? And then all the required probabilities can be calculated. We probably want to ask, well, how large is large enough? In practice, we say n greater than or equal to 30 is our threshold. As long as n is at least 30, then you can say it's large enough, and then you can apply this theorem and say your sample mean is normal. Okay? So I'm going to stop here, and my last word is that today what we're talking about is mainly the distribution of sample mean. If you know what we are doing, then basically we are deriving some properties of sample mean from the population, so that given the population distribution, we can calculate the probability for us to see some results of sample mean. For us to see that sample mean is greater than 2.2, the sample mean is less than 1.5, and so on and so on. Okay? And that's the foundation for further inference. Okay, let me stop here. Thank you.